Hi everyone. This is the second lecture on our lecture series on the analysis of capacitive charge sharing circuits with MOSFETs in place of resistors. In the previous lecture, we laid the basics which are very helpful in analyzing those circuits. In the first few minutes of this lecture, I'll again finish off the basics and we will start analyzing the circuits, slowly adding more and more complexity. So shown here is a diode connected MOS device, and we'll see what is the steady state behavior of a circuit like this. I've connected a voltage Vx which is equal to 2 volts at gate and drain. Both gate and drain are shorted. So in this circuit, you can directly see the drain to source and gate to source voltages are same, because since gate and drain are shorted, VGS and VDS are same. And the condition for the current to go to zero is VGS less than or equal to VTN, because you cannot have a condition where it is zero, because by then the device is cut off. So if the source voltage say is rising, you will reach a condition VGS less than or equal to VTN first before you go to VDS equal to 0 or VGS equal to 0. In fact, you will never reach a condition VGS equal to 0, because by the time the source voltage reaches a value so that VGS becomes less than VTN, the device will stop conducting. So if I apply 2 volts, the maximum voltage the source can go to is 2 minus VTN, in this case 0.5, which is 1.5 volts. So in fact, you can, since we called it a diode, you can just replace a MOSFET with a diode as shown here and analyze the circuit. So if I have connected a voltage Vx, say this Vx is greater than the cut-in voltage of the diode, and in this case it's VTN, the cut-in voltage. If it is greater than VTN, current will flow through the diode and it will charge this capacitor. Now the voltage across this capacitor will be Vx minus VTN. So the same thing holds here. So if I apply a voltage Vx which is greater than VTN, if I apply it to a diode connected MOS device, the maximum voltage this capacitor will be charged to will be Vx minus VTN. So that's it. This is all the basics that is necessary to understand and solve these circuits. I didn't even go to the ID versus VDS characteristics. You can easily think of it. A MOSFET is a square law device. Since gate and drain are shorted, the device will always be in saturation. Okay, so it will go from saturation to cutoff directly. So since VGS minus VT, VDS will always be greater than VGS minus VT. So this device will always be in saturation. In fact, the ID versus here VDS and VGS are the same. So ID versus VDS characteristic will be exactly same as ID versus VGS. So it's a square law device. So beta n VGS minus VTN the whole square by 2. But beta n is mu and C ox WL. So this is VGS and this is ID here. So the device, as the source voltage increases, the current will decrease, and this is the point where source voltage, VGS becomes equal to VTN, which is also equal to VDS. At that point, the conduction stops and the capacitor voltage stays at Vx minus VTN. So that's it. So this is all the basics